Thank you for the introduction. Hi, everyone. First of all, thanks for having me, and thanks to everyone for joining today. I am glad to give a talk in this EarthCARE Science Seminar Series. My name is Jiseob Kim, and I'm working as a postdoc at McGill University in Montreal, Canada. And before I start, I'd like to mention the people involved in this work. I'm working on this with my supervisor, Pavlos, and my colleague, Bernard, at McGill, and Alexandro from Polito in Italy, and Xipeng from Environment and Climate Change Canada. Thank you very much, and I'm glad. I also got a lot of helpful comment from the ESA EarthCARE disk teams, so I also want to thank them. So today I will talk about fast and falling ice particles observed by EarthCARE CPR. Okay, first thing first, I'd like to introduce the project behind this work. This study is supported by ESA, and it's a part of the BAMOS project, which is one of the EarthCARE Plus innovation missions. One of the key goals of BAMOS is to show what kind of new science is possible using CPR measurement. In particular, we focus on particle air motion and the hydrometer sedimentation velocity. I'm mainly working on sedimentation velocity studies, and after my talks, Ida will introduce another study focused on cloud dynamics in convective cloud. That will be interesting as well. Another important goal is to introduce these observations to different research fields. So personally, I think it would be really nice if more people from different communities start using the measurement through these seminars. So if you are interested, just feel free to visit this website or contact me directly. Okay, let's start. EarthCARE is a joint satellite mission between ESA and JAXA, and one of the key instruments is the CPR, the cloud radars, which was developed by JAXA. So JAXA has become the only agency that has 3 spaceborne cloud and precipitation radar, starting from TRIM PR, then GPM DPR, and now EarthCARE CPR. It's a really, really impressive achievement. And compared to cloud set CPRs, EarthCARE CPR has several improvements. For example, it provides a higher sensitivity and a higher resolution. But the most important difference is that EarthCARE CPR is the first spaceborne deployed cloud radars. So now we are observing the particular motion of particles inside the cloud from space for the first time. So the Doppler radar can provide the Doppler velocity, which measures whether the target is moving toward or away from the radar based on phase shift of the radar signals. For cloud radars, that means we can observe both the full velocity of a hydrometer and the particular motion. The example here is a mid-latitude cyclone observed between Greenland and Europe. The broad green regions mainly show falling ice particles. Most of them are around 1 meter per sec or less. The purple regions are mostly raindrops. These are falling faster, usually around 2, 3, or 4 meter per sec. And somewhere between them, so we roughly have the 0-degree isotopes. And we can also see some shallow cloud in lower part. There we can also observe some drizzle around 1 or 2 meter per sec. What's really interesting is that the satellite itself is moving at about 7.6 kilometer per sec, like this. But at the same time, it's measuring motions of only a few meters per sec from particle falling, so about 400 kilometers below. And if we only focus on ice particles, the difference we care about can become as small as a few centimeters per sec. So if you have ever looked at the low Doppler velocity field from the CPRs, you probably noticed that the data are pretty noisy. The estimated uncertainty of the level 1 Doppler velocity is larger than about 1.3 meter per sec, 1.3. So I would say it's very difficult to study subtle microphysical signals in ice cloud using only the load velocity. The two upper panels shows the carefully calibrated and corrected level 2 reflectivity and the flow velocity product. ESA and the JAXA independently produce their own level 2 product. And here I'm showing the ESA product. And we go one step further. The CCD algorithms removes the vertical air motion component from the flow velocity and estimate the sedimentation velocity. If you compare it with the flow velocity field, the sedimentation velocity looks much smoother and more stable. The estimated uncertainty is reduced to about 0.2 or 0.3 meter per sec in ice cloud, and the bias is close to 0. But the more important point is that this variable is mostly free from the vertical air motion. So it's much more suitable for studying cloud microphysics. All the results I will show today are based on these variables, and the paper describing this retrieval algorithm is currently being prepared by my colleague Bernard, and it will be submitted soon. One important point is that this algorithm is mainly designed for stratiform cloud, so in this study, I removed convective profiles in advance. Okay, so in this study, what I focus on is the particular gradient of sedimentation velocity. I call it ZV, and I reverse the sign so that positive value indicate acceleration of falling particles. This gradient gives us microphysical information and the context that we cannot get from the particular velocity itself. For examples, when ice particles grow by vapor depositions, the acceleration is usually small, typically around 0.1 and 0.2 meter per kilometers. This value comes from 1 year climatology using stratiform cloud observations. But when particles grow in a more fluffy way, like dendritic growth or aggregation, the velocity increase become very small. Sometimes the particle can even slow down. Rhyming is very different. When speckled liquid water rapidly stick to the ice particle surface, the particle mass increase very efficiently. So rhyming is expected to have the strongest accelerations. The photo on the right are snow particles on my clothes. I took myself in Little Italy in Montreal, which is great place for Italian food and espresso. Before having lunch there, I observed the rhymed stella plate. You can see that the rhyming starts from the particle edge and gradually covers the whole particles. This process increases the particle mass very efficiently, much more than the particle size. Then after lunch, I observed the dendritic aggregate instead. These particles were very loosely connected. So in this case, particle size increased efficiently, but mass increase is very relatively small. So basically, what we want to investigate is how these different growth processes appear in the sedimentation velocity gradient. So what you see here is a 1 year climatology of ice sedimentation velocity in stratiform cloud. The left panel shows the sedimentation velocity, and the right panel shows the vertical gradient. Overall, as the temperature increases from -60 to 0, the sedimentation velocity also gradually increased. But the interesting thing is these regions between -20 and -10 degrees. In this temperature range, the particles start to slow down. You can see this much more clearly in this gradient field. We only selected regions where reflectivity is increasing. So even though the particles are still growing, we still observe a deceleration in this temperature range. And actually, this kind of signature is very common in stratiform ice cloud around the globe, including the tropics, mid-latitude, and the polar regions. So this case shows how clearly these decelerations can appear in actual cloud. If you look at the refractivity field, it's hard to notice that something special is happening here. But if you look at the sedimentation velocity field, you can see that the fall velocity decrease around minus 20 degrees and then increase again. And in the bottom panels, you can clearly see this distinct deceleration band between minus 20 and minus 10 degrees. Interestingly, this temperature range matches with the dendritic growth zone. In these regions, ice supersaturation becomes very high, so ice particles grow very actively into dendrite or plate-like particles, and the aggregation also becomes very efficient here. So in this kind of growth process, the particle cross-sectional areas increase much faster than particle mass, so the particle become more like a small parachute. They experience much larger air drag. So even though the particles are still growing, their fall velocity can decrease. And this kind of deceleration may also affect precipitation efficiency and the cloud lifetimes, but current weather and the climate models still don't represent this picture very well. So how important this impact is in the models, I think that's still an open question. And a more detailed investigation about this is currently ongoing in Robin Hogan's CMWF teams using models and the EarthCARE and aircraft data. So, okay. Now I'd like to move to rhyming. As I mentioned earlier, rhyming is expected to have a stronger accelerations than other ice growth process. So we try to identify rhyming based on these features. But one of the most difficult part of this study was deciding the threshold for rhymings. So what I did was I focused on ice cloud, where rhyming is very unlikely. So basically, these are cloud where CPR and athlete both identify ice hydrometers, but where athlete does not detect supercooled liquid water. These darker regions, darker green region is that groups, but because athlete cannot penetrate very deeply into thick cloud, this group may underrepresent aggregations. But if you can see, if you see this in this previous slide figures, aggregation tends to show deceleration, and the gradient is slightly larger at the upper part than below. So I think this is still a reasonable non-rhyming reference groups. And what we found is that about 99% of these clouds have a gradient smaller than 0.4 meter per sec per kilometer. In other words, vapor deposition and the aggregation alone rarely produce acceleration rather than this value in stratiform cloud. So I use this value as a threshold for rhyming detection. The next step is to evaluate whether this threshold is actually related to rhyming. This is not very easy because we don't really have a comparable ground truth data for rhyming. So my approach was to estimate the mixed phase layer independently and then check whether the detected rhyming matches with that layers. The cloud system I'm using is the shallow mixed phase cloud over ocean. In this cloud, supercooled liquid water is usually concentrated near the cloud tops. And this gives us nice opportunity, very unique opportunities, because using only EarthCARE observation, we can roughly estimate both the supercooled liquid water layer and the liquid water path. First, the supercooled liquid water top is detected by athlete, the black dot here. Then using the path integrated attenuation from CPRs, we can estimate the liquid water path. This is based on liquid absorption models. If we know the temperature-dependent liquid absorption coefficient, we can drive a liquid water path from the PIA based on this relationship. And of course, this assumes that the clouds are fully below 0 degrees. And then using adiabatic relations, we estimate the liquid water depth from the liquid water path. And from that, we can also estimate the supercooled liquid water base, the white dot here. So you can see that the strong gradient regions, the dark blue areas, are mostly located between the estimated supercooled liquid water tops and the base. So this figure shows the rhyming probability from 1 year shallow mixed phase crowd observations. The x-axis is the supercooled liquid water path, and the y-axis is the distance below the supercooled liquid water tops. The dashed line shows the estimated liquid base. This is only an example, so I mean an estimate. So it does not mean that supercooled liquid water always exists only inside these layers, but statistically, it is probably concentrated there. As liquid water paths increase, the liquid water layers become deeper, and the rhyming probability also increase. When liquid water paths become larger than about 200 gram per square meters, the rhyming probability it exceeds about 50%. 200 is a bit large values for shallow mixed phase crowd. Typically, the average value is close to here, 50. And in that environment, rhyming probability is only around 20%. This may mean the rhyming is actually not happening very often there, or that only weak rhyming is occurring, which is too weak for this method to detect. But overall, since rhyming efficiency is generally related to liquid water paths, I think this is still a pretty reasonable result. But of course, the best way to check whether this is really rhyming is to compare it with the aircraft in situ observations. During a call-up campaign, the NRC Conveyor 580 aircraft observed the mixed phase crowd in Quebec at the same time as EarthCARE. The left panel shows the aircraft radar reflectivity and the blow velocity, and the right panel shows the CPR reflectivity and the sedimentation velocity. The horizontal line at 2 kilometer height is the aircraft altitude, and this vertical line is EarthCARE overpass point. During this flight leg, the overall crowd structure looks pretty similar between the two radar. What makes this case really interesting is that to the left over the overpass point, the crowd is mostly mixed phase crowd, but to the right, it becomes mostly ice phase. We know this from the aircraft liquid water content measurement, but I didn't include them in this slide though. Anyway, if you look at point A and point B, the aircraft observed a large amount of supercooled liquid water there, and some rhymed particles were also observed. If you look at the blue rhyming detection regions I detected, you can see that the CPR-based method also detects rhyming near A and B. At A, the rhyming is mainly detected near the upper part, and at B, it is detected more from below. We are still investigating why it is different appear. But if you look at point D here, there is almost no rhyming detections around that area, right? And the aircraft also did not observe supercooled liquid water or rhymed particle there, even though athletes still detect supercooled liquid water near the crowd tops. So in this case, it seems that the supercooled liquid water was mainly consumed by vapor depositional growth through the WBF process. Then at point C, slightly rhymed dendrite were observed, but my method only detected rhyming below that area and missed the upper part. Probably because the ice crystal were already relatively massive there, so the additional mass gain from rhyming was relatively small. So overall, the CPR-based rhyming detection method does not capture all rhyming cases, but in supercooled liquid water rich environment, it seems to detect rhyming reasonably very well. So this slide shows an example of applying the method to deeper crowd system, the black dot. indicate the highest layers where athlete detects liquid waters, and the blue region in the bottom panels are the rhyming regions detected by our method. You can see some rhyming near the cloud tops over the shallow mixed phase cloud and the deeper cloud. And if you there is also rhyming regions here, even though these regions where athlete cannot penetrate. But sedimentation velocity there is often larger than about 1.5 meter per second. So I think it's quite reasonable to say that rhymed particles are there. So this is one of the biggest advantages of this method. It can detect rhyming and the mixed phase layers, even in regions where athlete cannot penetrate. So this is the last slide. This slide shows the global rhyming probability map from 1 year of data. As I mentioned earlier, the convective cloud were excluded from this analysis. So in the tropic, rhyming is not very frequently detected. The main rhyming hotspot appears over Northwest Atlantic and the Nordic Sea, Europe, and the Northwest Pacific, and Sichuan Basin in China, and also Southern Ocean. And these regions are generally consistent with the region where Calliope previously observed the pre-country liquid waters. Personally, I think Sichuan Basin in China is especially interesting. To the west of these regions, we have the Tibet Plateau here. The westerly flow is blocked by the plateau and split into two branches. Then the flow merges again near the Sichuan Basin and they form a frontal system. And there, so we often observe very broad and horizontally flat rhyming layers. So I'd like to say that rhyming is not random. It usually requires some mechanism that support and sustain the mixed phase environment. So this could be frontal lifting, waves over turbulence driven by cloud radiation interaction. And in stratum cloud, rhyming is actually a very efficient process for producing heavy precipitation. So I think rhyming is a very important process for weather and climate models. And we believe EarthCARE can provide a useful observational constraint for evaluating this process. Okay, just to summary, I'd like to highlight that sedimentation velocity and its gradient can provide a lot of information about how ice particle grows. And using these features, we can now start looking at rhyming and the other ice cross processes globally from space for the first time. Some people may say that data are still too noisy, but EarthCARE is already revealing these kind of subtle microphysical features. So that we didn't even expect when this mission was first planned. So I think there are still many things left to discover from these observations. One of the next steps is to better understand which environment favors or suppress rhyming or other ice growth process. And another important direction is to better constrain the mass size relationship of rhymed particles in EarthCARE microphysical retrievers. Eventually, we want to provide useful observational constraints that help model better represent real cloud microphysical process in nature. Okay, thank you very much. Thank you for your listening. Thank you.